Welcome to This Explainer. Today we're diving straight into the hidden logic of technical drawing to discover exactly how abstract ideas are reliably transformed into physical reality. Have you ever stopped to wonder how a simple piece of paper, just lines and numbers, can actively guide the engineering design of something as massive as a skyscraper or as complex as a jet engine? Well, that's exactly what we're going to decode right now.
Seriously, think about the incredible journey of an engineered part. It has to cross this massive gap, from the complex imagination of a designer sitting at a desk all the way to a manufacturer's bustling factory floor. And the crazy thing? It has to do this without a single word actually being spoken between them. No quick phone calls, no clarifying emails. So how is that level of perfect, silent communication even possible? Well, it all comes down to a highly standardized visual vocabulary.
And that brings us to the formal definition, straight from the international standard ISO 129. A dimension is, technically speaking, a numerical value expressed in appropriate units and indicated graphically with lines, symbols, and notes. But what does that actually mean for us? Essentially, dimensions act as the ultimate, unambiguous translation guide for engineering design. They're the exact, non-negotiable instructions that literally tell the physical world how to shape itself around an idea.
To get a handle on this, we're going to cover a few key areas: the universal engineering language, anatomy of a dimension, defining what truly matters, arranging for precision, and finally, navigating special shapes.
Let's kick things off with Section 1, the universal engineering language. We really have to establish the absolute necessity of a standardized language across all fields, from mechanical to civil engineering. Without these standard rules, chaos would completely reign on the production floor. The standard dictates that this visual language applies across the board. A drawing must define a part completely, no guessing allowed, ever. It uses one uniform unit throughout the entire drawing, often millimeters, entirely without writing the unit symbol. This keeps things incredibly clean. Dimensions are placed for maximum clarity, and crucially, each feature is dimensioned only once. This prevents a total nightmare scenario where conflicting measurements ruin a part. Everything you need is right there, ensuring the original engineering design is perfectly preserved without needing any outside documentation.
Moving right along to Section 2, anatomy of a dimension.
Okay, let's break down the actual visual components that make up this engineering alphabet. Just like sentences need nouns, verbs, and punctuation to make any sense, a technical drawing relies on specific lines and symbols to convey undeniable meaning. The core elements we're looking at include projection lines, dimension lines, leader lines, origin indications, terminations, and of course the dimensional value itself. When you see how these basic elements work together in practice, it really clicks. You've got thin projection lines that extend just slightly beyond the horizontal dimension line. At the ends of that dimension line, you have specific terminations, like crisp arrowheads pointing exactly to the boundaries. Or, alternatively, you might see an oblique stroke, which is super common in architectural and civil drawings. It's a precise, locked-in visual grammar designed specifically to avoid any misreading.
All right, Section 3, defining what truly matters.
Let's connect this grammar directly back to how it guides engineering design, because here's the thing, not all dimensions carry the same weight. We really must draw a stark contrast here. On one hand, we have functional dimensions. These are absolutely 100% essential to the part working at all or fitting properly into an assembly. On the other hand, we have non-functional dimensions. These are simply convenient for the production or inspection of the piece, but they don't actually dictate its ultimate success or failure in the machine.
A classic example of this is a shoulder screw. The crucial functional dimensions, often explicitly labeled with an F, like the diameter of the smooth shaft that actually bears the load, are prioritized and placed directly into the design specs. The whole point here is that by directly dimensioning these key functional features, the designer physically stops the manufacturer from trying to calculate it indirectly. Why? Because indirect calculation can introduce dangerous stacked tolerances that would completely ruin the incredibly tight fit required for that screw to function. In short, the dimensions literally guide the engineering intent right into the metal.
Which leads us perfectly into Section 4, arranging for precision.
Moving from individual elements to entire structures, the actual arrangement of these numbers dictates the precision on the floor. Take chain dimensioning, for example. This is where dimensions are placed end to end, kind of like links in a chain. While it looks super neat and organized, we have to caution that it should only be used where the potential accumulation of small manufacturing errors won't absolutely ruin the final product. Think about it. If the cutting tool is off by ½ millimeter on the first cut and another ½ millimeter on the second, suddenly your final feature is off by a full millimeter, and that can be a real deal breaker.
So, to build a much safer solution and prevent that dangerous stacking of errors, engineers rely on parallel dimensioning. This is where all the horizontal dimensions start from one single common vertical feature, a baseline or origin plane. By measuring absolutely everything from this one common baseline, you ensure total, non-accumulating accuracy for every single step of the machining process. It's a total game changer for precision.
Let's wrap up our deep dive with Section 5, Navigating Special Shapes.
Just like any spoken language has exceptions and unique adaptations, this visual language has very specific rules for complex shapes. Take curves, for example. A curved radius requires only a single arrowhead touching the arc, combined with the letter R right before the number. It's honestly incredibly elegant. It perfectly proves how the standard actively minimizes visual clutter on the page while simultaneously maximizing clarity for the machinist trying to actually cut that specific curve.
Now, what about repetition? For repeated, equidistant features, like a long series of evenly spaced holes, the visual language smartly adapts into a sort of mathematical summary. Instead of dimensioning the space between every single hole and completely crowding the drawing, it simply states the formula, like 5 times 18 equals 90. This saves massive amounts of space on the paper and prevents the manufacturer from getting bogged down reading redundant, confusing numbers.
Shifting gears over to civil engineering and architecture, we can see how the language adapts for massive physical space. Instead of using dimension lines that span an entire building, we use elevation levels. This involves a specific closed arrowhead that dictates a vertical elevation based off of a predefined base zero ground level. So whether you're dealing with a tiny machine part or a massive multi-story building, the core principles of clarity remain exactly the same.
I really want to highlight a quote directly from the standard because it perfectly summarizes the core philosophy of everything we've looked at today. It says, "All dimensional information necessary to define a part or a component clearly and completely shall be shown directly on a drawing. A manufacturer should never have to guess, assume, or pull out a calculator. The design intent and exactly how it must be built is permanently and safely locked right there into the dimensions."
So I want to leave you with this final thought. What happens when this universal language is misunderstood? Really think about it for a second. A missed functional dimension or a misread parallel line isn't just a simple typo on a piece of paper. It's a bridge that doesn't align. It's a spacecraft engine that fails under immense pressure. Or it's a medical device that just doesn't operate correctly. The real-world stakes of engineering communication are absolutely massive. So the next time you look at the designed world around you, from the phone in your hand to the building you're sitting in right now, take a moment to appreciate the silent, universal language of dimensions that made it all perfectly possible. Thanks so much for exploring this with me.